guess you got all you wanted. Yeah, I don't know why suddenly you're gone. You'll never be forgotten. Pretending no one is to blame. Too late to reignite our flame. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind. Guess all you left me blind. Guess all you left me blind. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind. In retrospect, I could have paid attention. I could have tried harder, been smarter, deep water, I'd be drowned. I should have felt the tension. I overreacted and acted childish, impacted us all around. When you were pushing me away, I should have tried to give you space and get out of your way. How did I not see this coming? You leaving one day. Pretending no one is to blame. Too late to reignite our flame. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind. Guess all you left me blind. Guess all you left me blind. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind. How did I not see you running? How did I get behind? How did I not see this coming? Guess all you left me blind.
Hey folks, how you doing today? No, we're doing efficiency of algorithms tonight. That should be on schedule. We did the ADT bag yesterday. We're just finishing up the last little bit of chapter 3 today. Oh, nice. Yeah, we don't need those ads, thanks. We'll mute those ads, let them finish. How you doing, folks? Sorry to be running late here. This was a crazy day. So thanks for being flexible. And actually, chapter 4, it's not as long as some of the other content. So we should be okay. We shouldn't end up running super long tonight. So it should work out in the end that we started a little bit late. Yeah, did I mess up the title? I thought I changed it to efficiency of algorithms. Let's see. Do I have a title? Yeah, there we go. Look at that. Nightbot is so helpful. Thank you, Nightbot. All right. Yes, we'll talk the last little bit about the linked objects bag from chapter 3. I think we got it all finished. We'll go over it again, and then we'll look at, someone had questions about how we can loop through using that to array, because it was not working. Turns out it actually doesn't work like I thought it would. So Java's just dumb. And you just get that object array like we had, and that's okay. So efficiency of algorithms is all about how we talk about how efficient algorithms are. That's looking at that. And that's what we'll talk about tonight. And it turns out I also forgot to post the quiz. So apologies for that. I'll work on, and it's fine because we'll review chapter 3 tonight as well. So we'll have a quiz coming up. There we go. I can unmute and give that a pause. There we go. Awesome. All right. So So I got NetBeans here. We got our ADT bag project. Close this other one here. And we'll take a look, quick little review, looping through each object. So when we use the toArray, right, it's not giving us the proper type. Again, apparently that's how it's supposed to work. Yeah, quizzes are open book, open notes, open internet. Just cite your sources if it's not from the book. And if it is from the book and you're giving me a direct quote, obviously that should be in quotation marks. Right? But I'm assuming you're using the book as the resource for answering the quiz questions. Because anything in the chapters is fair game. All right, your idea is to read the textbook. It's your main reference for the course. I'm pulling out the highlights here. So anything in the text from the chapters we covered is fair game for the quizzes. All right, and I'll work on getting that. So what we can do, if we have this objects array here, we want to turn them back into the correct type. Right, like this result is my linked names toArray. I would then want to cast it here as the type. So we can say, hey, I actually want this as a string. So we'll cast it as a string. In this, it wasn't actual. It's not an item or anything like that, but we could, like this idea with this item class in the shopping cart, which has a bag of items. This kind of idea. So this was for the project, right, where you can give it any kind of bag interface. It doesn't care how we do it behind the scenes. We could either use our bag array or a bag of linked objects with this internal node storage. This is where we want to spend some more time looking at this node storage, because we're going to spend a lot of time looking at nodes and why these are important. And the whole idea is that one object knows where the next one is. And we'll look at expanding that as we go a little bit as well, which is really fun. So you can do a lot with this idea of one object knows where the next one is. So one object references the other, right? Because that way you don't need a contiguous block of memory. You don't have to tell Java to ask the operating system for a chunk of memory that can hold 1,000 of these things. We just make nodes as we go, just adding one at a time and just adding more references. Right? So they're very efficient in that sorts of manner. They grow very easily. And we'll look at all the trade-offs as we go as well. And that's why we need to get to chapter 4, this efficiency of algorithms, for that conversation to make a lot of sense. So let me go to a tab up here. Oh, and I did find all of the PowerPoints for the book. I didn't have them previously, but I found them, put them up there for you. So if you go to content and take a look at the textbook slides, I've got all the chapters, all the preludes, all the interludes as well, right? And then the chapters themselves. Now you're going to have to use this load more button, because there's a bunch of them here as we go through all of our chapters, okay? And then the appendices as well. Right, so they're all out here for you if you like the book PowerPoints. So those should all be out there for you. The T, yep, so T is the generic idea. So when you say something is of type T, we're saying it's a generic type. So this class can be used for any given type here. So like when we went to, we looked at our array list. Oh, I think I got rid of that, didn't I? If we look at array list. So this is the one hopefully you've seen before, array list. And you tell it, hey, I want it to be of a certain type. So an array list of type string. Or, let's even do item, right? It's going to be an array list of type item. This is our items. There's a new array list. Like that. So this was built into the Java library, right? The java.util.ArrayList. And you might notice it's an array-backed list. That's why it's called an array list. It's using this as type of item here. So this is the generic type. So we can do that same thing, right, when we make our generics. So if we write a class that can have some sort of generic type, we'll say it's T using these greater than, less than signs, or diamond operator, I think is how we refer to that. And then what that means is when you declare it of this type, the T, everywhere else we use it, becomes that type as well. So we can say, hey, you can add a T of this item. So as long as it's the type that you declared, we can add that type. And the benefit of that is that we get compile time checking. Right? So that when I try and add something, I can make an item, item equals new item. And then I can say items.add, I can add the item. Right? But what I can't do is I can't add a string. I try it, that should be say item, not time. New item. It's going to be upset with me, and it won't even compile now because it says incompatible type. String cannot be converted to item. So by using a generic type and declaring it in code, we get compile time checking. Right? The alternative to that is we could have an array list of type object. Now, this is objects or something. Equals a new array list. Now, everything is an object, right? Because every class inherits from object explicitly, or implicitly, I'm sorry, implicitly inherits from object. I always get those mixed up, I'm sorry. So we could add anything we want here. So I can take my objects and I can add item. I can take my objects and I can add a string. I can take my objects and I can add an integer. I can add 42 because they're all of type object. And remember, you get this automatic boxing and unboxing happening. It's not the primitive int 42. It's actually the class integer storing the value of 42 with the boxing and unboxing stuff. So array list of type object does not give you compile time checking versus a array list of a generic type, which we're declaring is of type item. Gives us compile time checking, and that's the big benefit here. Ooh, yeah, coffee. I'll throw out that coffee emote. Okay. Does that make sense, Ray? Posture check. Thank you so much. Thanks for the reminding me about the @ here, Professor Perp. And that's only going to remind people who are online, right? They're going to be actively on in Discord. Cool. Doesn't work. Not the right type. Yeah, they're active in that channel. Also, does that mean you haven't muted the channel? Right? Because you could be on Discord, like because your default in all of the channels in Discord, right? I don't know. Sometimes I feel like I should just add roles and then have people message me to add the right role, but that feels like a lot more work than it's worth. Oh, Code, thank you so much for the hydration. Yeah, cheers. I got my iced coffee. This is number 3 or 4, I forget. I already finished this one. That one's empty, which is sad. Yeah, the MeBot. That way everyone can self-assign a role. That makes sense. I mean, I don't know if people are going to do it. maybe I'm just a pessimist that thinking people would go and assign themselves the correct role. But I figured they'd just be in the right channel. I don't know, but wouldn't know to mute the others. Oh, like if you lock everything else down? Yeah, you could lock everything else down. Well, Professor Perp, you would think I'd have no issues, but it's going to cause a lot of emails to me. Just that's my assumption. So as any good developer, I am efficiently lazy, and I don't like to do more things than I need to do. So what we'll call the current Discord the minimum viable product. There's definitely opportunities for improvement, though. Definitely, we'll put those on the backlog. Okay, so let me get GitHub open here, and we can go take a look here. Oh, yeah, good. I'm already in the right repo. 2353. So we added some new. This is generics versus objects. All right. Cool. Any other questions, I guess, while we're here, about project number 1, which is due next week by 6 p.m.? Remember, at 6 p.m., I'll be going over the solution to it, so I can't take it late. Right? So turn in what you have, and there's definitely partial points for that if you have some of it done but not all of it. So whatever you've got done, get it to me by 6 p.m., and we're good to go. Yeah, it's laggy. What is going on? I moved my fan. Now I think my computer's just running too hot. I'll kill Spotify. project number 1 is worth 10 points here. So all of the projects should have a rubric attached. And I would like you to do a self-assessment. So you're welcome to just number them. Say, hey, for number 1, I got a point. Number 2, I got a point. Or copy paste, whatever works well for you. But I found I've been adding rubrics all the time. And people still wonder whether or not they are going to get points for certain things. So I've started asking for a self-assessment and like, hey, go look at the rubric and did you do this thing? Did you do this thing? Right, so our shopping cart accepts the bag T interface object in the constructor. Right, I gave that one to you. Right, this is our shopping cart. It accepts a type of bag interface. So because it's a type of bag interface, any class that implements that interface can be provided here, whether or not it's our bag array or our bag of linked objects, or we can even write another one, right? Anything that implements this interface is fine because it fits this, because through polymorphism, right, this idea that you can treat an object as another type, anything that implements this interface is polymorphically one of these things, right? It's implementing an interface is very similar to inheritance, where you are a, or it creates that is a relationship. So a bag array is a type of bag interface because it's implementing the interface. So we can treat it polymorphically as its interface type. And it has all the methods in bag interface. We can do all these same things regardless of which type we gave it. So for the shopping cart, right, it's still going to do the exact same thing because the bag interface acts the exact same way. It has the exact same methods regardless of what happens behind the scenes. All right, so let's take a look at Chapter 4. So Chapter 4 is a lot of fun. It starts looking at efficiency, right, and whether or not our code is behaving in an efficient manner, right, and how fast things are running, that sort of thing. And how do we even measure it? So if you take a look at, this is a really good example. I like this one here. So let me add, let's do a new project. Let's do a Java with Ant project for Chapter 4 in the 2353 folder. So this will put it in my repository. Right? If you put something in your repository folder, Git's going to say, hey, I see a bunch of new stuff. Yeah, I don't know if it's Comcast at this point, Professor Perp, or just my Wi-Fi, or because I've been meaning to run a cable up to my office, but I don't really have the motivation to drill through the floor and the ceiling to run the cable up to my second floor office. So, that's all. All right. So looking at Chapter 4, right, this is all about efficiency of algorithms. Let's look at some different ways to generate a sum. So we'll make a public int sum of numbers up to n, given an int n. Right? Or, I don't know, from 1 to n, maybe from 1 to n is probably better. Sum of numbers from 1 to n. So if I asked you to give me the sum of all the numbers from 1 to n, right, you're probably going to think, okay, we'll have an int sum start at 0, and then we'll loop. We'll say for int, I don't know, current is 1, current is less than n, current plus plus, and we'll take sum plus equals current. And when we're done, we can return sum. Right, and we could try it here, right? If we take 5 plus 4 plus 3 plus 2 plus 1, this should be 15, right? 1 and 4 are 5, 2 and 3 are 5, and 5 is 5. Right, so it should be 15. So let's print what we get back out. So sum of numbers, nope. Sum of numbers, oops, static, there we go. If it's static, I can get to it. Sum of numbers up to 5. We should get 15. Again, this is poor man's testing, right? We're going to just eyeball it here instead of writing some unit tests. That'd be more proper. Maybe we could do that. We're going to need this in main here in a minute. Oops, I got 10. I didn't get 15 because I stopped at less than n. So if I did less than or equal to n, that would probably give me the 15. See, it's always good to test your code. I totally did that on purpose. So now we get 15. Okay, so if we think about how long this takes to run, so let's go, I don't know, let's do like 1,000 for fun. right? How many times, how many operations does the computer need to do to calculate that it's 500,500? Well, our loop is going to run 1,000 times, right? Because it is going up to n. So in terms of performance, right, we would say that this one takes, the bigger n is, the more operations this one has to do. So there's a term we use, which is called big O. It's omega, I believe. It probably even says it in here. Yeah, big O. Microsoft calls it O. I think it stands for omega, maybe not. So big O is all about how do we measure the performance of our code. So this one is in terms of time complexity. We haven't talked about space complexity, but there's a space complexity as well, which is referring to how much memory it uses. So our time complexity is how long it takes, and our space complexity is how much memory it takes. So for this one here, right, it's big O here, which is just a capital O. You'd say of a certain value. In this case, is of n. Right? The bigger n is, the more operations it has to take. If we're summing up to 1, it takes 1 operation. Up to 1,000, 1,000 operations. Up to 1,000,000 operations. Right? So that's how we can talk about its efficiency of the algorithm here. Now, an easier way to do this, static int sum of numbers from 1 to n better, given an int n. If you've gotten far enough along in your math classes, you might recall that we can just return n times n plus 1 divided by 2. And this is a math thing you'll learn eventually. Don't worry about it if it doesn't ring any bells right now. So to sum numbers from 1 to n, you can just do a single operation. So addition, multiplication, division. So like it's one thing, two things, three things. But the bigger n is, Java doesn't care, right? It's still doing this same 3 numbers of things here. So that's a constant time. So we'll say, again, it's O of essentially 1. A fun thing you get to do when you start looking at efficiency of algorithms is you can essentially throw away the coefficient. So like if it has to do 3 things for every n, right? That's the coefficient is 3 here, 3 times n. We just get to throw that away. If it's really 3 operations, we essentially just throw it away and say it's 1. So anything that is a constant number of operations, we'll say is O of 1. So it doesn't matter how big n is, it's still the same number of operations. In this case here, it's still going on here. The sum of even or odd numbers up to n, I can do it this way. I don't know if there's a math trick for it. I would just check here, like say if current, mod 2 is 0, then I'd go add, right, for even. If you want an odd, if it's 1, that sort of thing. That's probably how I do it. There might be a faster way, like mathematically, to get a constant time operation, but not really sure. Well, what would it be? So like all the odd numbers are just 1 more than the even numbers. I'm sure there's some trick. That must be a fun math puzzle, but that's not. Yeah. Okay, so this one here takes n operations. Right, so the bigger n is, the more operations it has to do, right? All right, now we get into some terrible looking math, and that's okay. Where we talk about our big N notation. There's a couple performance ones that we care about. So in terms of operations, you care about best time, average time, and worst time. Most of the time, we only really care about average. That's the most important one. Worst case performance is important. It's good to know, like, hey, if it is in the worst possible shape, how long could this take? But we almost never care about best case performance because it only is ever going to happen in the best possible case. So most of the time we don't care about best case. Average is the most important, and it's good to know worst case performance when we talk about how long things take. So if we looked at our bag interface here, right? we can look and see how long is it going to take to do these operations. So we'll take a look at the array-based implementation. So to get current size, it's constant, right? So this is an O of 1, right? Constant. So no matter how many items we have in here, constant, yeah, constant, right? It's only going to take one operation. Same with this empty. It's only going to take one operation. To add something, it only takes essentially, I mean, this is like 3 different things it's doing, but again, it's constant, so we'll say it's O of 1. For removing a random item, again, it's constant time. It doesn't matter how many n we have in here, we're just going to remove it. We're going to take the last item out and remove it. To remove a given t item. Now, this is where it gets fun, right? Because I don't know where this t item is in position to how many items I have in the bag. Right? So if I have 10,000 items in the bag and you're removing the first item, the best possible performance of this is O of 1. But again, best case is garbage, essentially, because we don't really care what the best case is. The worst possible case is the item doesn't even exist in there. I have to look at every single item in my list here, or in my bag, all n items, and I don't find it. So the worst case is O of n. On average, we'll probably say if you're looking for an item that's in the bag, the average time is probably going to be in the middle, right? Because half the time it'll be before the middle, half the time it'll be after the middle, so the average will be middle. And so to say the average here is like 1/2 of n, right? Half is a coefficient. We throw coefficients away, right? So we say this is an O of n operation. And O of n also has another term called linear. This is a linear operation. So the more n there are, the longer this takes, right? Imagine you're graphing this out. So if we get our little whiteboard out here. Oh, my coffee. I'm going to have to run down and get some more in a minute. Right, so if we look at, this is size, or maybe not size, how about number of items, right? Number of items. And this is operations. Nope, that's the wrong direction. I'm sorry. I'm backwards. This is number of items. And this is number of operations. Operations. Right? So a constant here, right, this is constant, or O of 1 here. So it doesn't matter how many items you have. It's constant. Linear, right, is a straight line. Right, that's O of n, linear. Right, so the more n you have, the more operations you do. Excuse me. Okay, so the more items I have in the bag, the longer this is going to take. To clear, oh, we're removing one at a time. So this one is an O of n, a linear operation. We have to remove each individual item. All right, and remove just removes one. So we have to do a constant thing n times, which is n. Get frequency of, well, it's going to look at all n items. So it's O of n, right? Because I have to look at every single item in the list. And this best, worst, and average are all exactly O of n, because I have to look at every single item no matter what. Contains here is different, right? Contains, the best case could be, hey, it's the first item, I found it, return true. Worst case is it doesn't exist at all, I return false. On average, halfway through I find it, halfway through I don't, or half or near the end, half near the beginning. It's half of n, which again is just O of n linear. We throw away the coefficients. To array is O of n operations, right? We make a new array here, and we grab each one and we assign it. It takes n operations, O of n. Does that part make sense? Okay, now what we didn't do is we didn't make this resizable. So the book will go through and he'll actually make another class that makes it resizable. I think it's probably fine for us to be able to resize ourselves. So instead of saying, hey, I'm going to, if I am at my max, return false and does not do it, what I'm going to do is I'm going to resize. So I think that's a better way to go about this. So let's take a look at that. Let's see if we can do that. So if we're at our max here, then what we need to do is we're going to call increase capacity. then we can assign our method here, or then we can assign it to our array. So increase capacity, then we need to write, what is this method going to do? Well, remember, you can't resize an array. Oops, that was the wrong thing. Nope. Just slide. There we go, slide. So with an array, right, say I have my 20 items in here, or whatever our capacity was going to be, right? We put in, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just easy to have some numbers here. So to resize, what we need to do, we need to make a bigger array, and we need to copy all of these things into the new array. Okay, and we'll take a quick look here. So if we were to resize and just add one space here, well, to copy something, to copy my array, and to take every item and put it in a new array would be n operations. That's essentially O of n is slow. It does get slower, and we'll look at some of those in a minute. But an operation that takes n operations based on how big it is going to be really slow. And then if I want to add like 1,000,000 things to this array, what's going to happen? Well, when I add the 10th thing, it's going to resize, take 10 operations. When I add the 11th thing, it's going to take 10 operations to copy, plus adding the 11th. The 12th adding 12 will take 12 more operations. And you're going to get this really, really, really slow operation happening, trying to add a bunch of things to your array. So it turns out that people who are really smart at this sort of thing and know a lot of math said the best way to resize is you want to double in space. You want to double in size. So if we start with, say, size of 10, I'm going to make a new one of size of 20, right? Copy those 10 things down, right? Copy them all over, and then I've got space for 10 more. Then if I need more space, I'll make one of size 40, right? Make it a 40, copy all those ones down, and I've got another 20 more to go. So what happens here is really cool. So if you were to graph it out, yeah, Noctis, exclam class for more information. If we were to graph this out, and we were to say this is my number of items, and this was the number of operations. Okay, so if we default our capacity here to, what do we say? Our default capacity was 25. Sure. And you know what, 25 is a lot. Let's stick with 10. That's probably easier. So to add one thing is one operation. One thing is one operation. 3 things, 4 things, 5 things, 6 things, 7 things, 8 things, 9 things, 10 things. We had room for all 10. Great. The 11th thing now has to do 10 copies. So now I have 10 copies. The 12th item goes in because now we have size 20. Right? So we get to put in 10 more things here. Right? And then that one now has to copy 20 items. Okay? Then what has to happen is I can put in 20 more items. And then I have to copy 40 things. So if we're doubling in size every time, this works out really well. And the worst case performance then is n operations, right? O of n. It took us n operations, so we had to copy everything. The average time actually works out to be constant, which is super cool. So the average here is O of 1, constant time. And I'll show you that in a second. There's some math to prove that, which is really cool. Yep, a whole semester. So if you were to imagine this graph here, right, and this idea that we have to do these extra operations every time because we need to resize. This bar here, right, was 10. You can imagine this bar. Oh, it's no bother, Noctis. Exclam class for more information. So this bar here with this 10 operations, if you would imagine like tipping it down and laying it flat this way, it's going to bump all of these out to 2 on average. Right? This one here, where we have to copy 20 things, this bar here, if you were to lay it down, I drew this poorly, I'm sorry, would again bring this up to an average of 2 operations. Because you have room for 20 more once we've copied the 20 things, because we've doubled in size. This long bar here, right, we have room now for 80 operations. Just imagine that bar laying down. Again, we're at an average of 2 operations per add. So because we're doubling in this geometric fashion, right, where we're just doubling in size, that's a geometric growth, we get to say our average time here for adding is O of 1. It's constant because we're averaging out those ones that are slow, they average out on all of the other adds. And this only works if we do a doubling here, because our 10 operations that we spent here, we can average across the next 10 adds to say, oh, that's just 2 operations. This operation here that was 20 will average across the next 20, right? So that was 10 here, and that was 10 there. This was 20 there, this was 20 here, right? We just say, oh, it was slow once, but on average, right, when we lay that flat, it means all of those adds across 20 through 40 only took 2 operations each on average. So that's really cool. So that's if we do the doubling growth. So we're going to say instead of O of 1 constant, right? That's it, which is average, right? So again, this is average time for increasing capacity. So then we need to go figure out how do we increase capacity. So again, this is probably a private helper method. Some people think all the public methods go at the top. Some people say whatever, that's fine. I'm just going to use the NetBeans tool and so I'm going to create a method. And it makes a method for me. Let's see, where did I put it? Down here. Private method, which is great. This is not a publicly available method. We don't need something like that. We don't need anything publicly available. What we need to do is we need to go make a new array. So this array of items given a size here. So I have a T array of, this is new items, and I don't want to go with my number of items because I want to double. I want number of items times 2. Right, that will double my size here. Then I need to loop through. So for int index is 0, index is less than the number of items, index plus plus, oops, missed a semicolon. We're going to go through, we're going to copy, we're going to take my new items at index is equal to the items at index. Once I've copied them all over, I can say items is equal to the new items. We've now increased our capacity. We've doubled our size. Right, so we make a new array of twice the size, copy over. This again, this takes n operations, right? So again, this is an O of n here, O of n linear operation. Because the more n I have, the more I have to copy, right? If I'm at 10, I have 10 to copy. If I'm at 20, I have 20 to copy. If I'm at 40, I have 40 to copy. On and on and on and on. Right? But I only have to do it every time I double. So again, we get to average it out. So that math gets a little funny, but again, just kind of imagine this picture. This is how I always remember it here. We can average it out because we're doing the doubling. Just lay down the spikes, lay them down, and they average out perfectly. It's really nice. Okay. You with me so far? So in terms of how we're talking about these operations, so that should be all we have to do for our resizable here. So if we add, if we hit our max, increase the capacity, and then we can just keep on going here. So we'll take a look. I think we had some tests for this one, right? Do we have any bag array tests that returned false? No, we didn't end up writing the rest of them. So if we had a unit test that expected it to return false once we hit capacity, we'd have to go change that. But we don't have that. So, you know, that's the nice thing about unit tests. If you change the behavior, a unit test should start failing because we had a test for that behavior. Okay. Let's see, where did that go? All right, there is one worse way of doing this, and we're going to take a look at that one now. This is fun. Public static int sum of numbers from 1 to n bad int n. All right, and the way that you do this one, we'll say for int number, or we'll say current equals 1, current is less than n, current plus plus. Right, now what we want to do is we want to add the number 1. Because we don't want to use current here. We want to count up to current. It's totally contrived, but we could do it. We could say for int 1 is 1, 1 is less than current, 1 plus plus. Well, we need sum again here. So we'll say int sum starts off with 0, we'll say sum plus plus. So for the number 1, oh, and we got to go equals to here, right? Equals. So at 1, we'll run 1 time. The inner loop will fire, start at 1. It's less than or equal to 1, adds 1. Now at current 1, this loop is done. It goes back to here. We're done with 1. Now if we said like 5, so let's kind of sketch this out here. So looking, oops, man, slide. I keep using the wrong button to slide. So it's a terrible, terrible method, but it just gives us an example here. So to count up the sum of 5, right? That's 5 plus 4 plus 3 plus 2 plus 1, which is 1 plus 1 plus 1 plus 1 plus 1. Is that right? Plus 1 plus 1 plus 1 plus 1. 4 is 1 plus 1 plus 1 plus 1 plus 1. 3 is 1 plus 1 plus 1. 2 is 1 plus 1, and 1 is 1. We could do that. Totally fine. Hopefully you get the feeling that this is terribly slow here. And what's happening now is, right, for every n, for every value up to n, we have to do this loop here up to that number. So what we get out of it here then, right, we're going to get 5 plus 4 plus 3 plus 2 plus 1, right, which is, we actually, that's exactly what we were summing. We get 15 operations. So if we kind of chart this out right here, and this is, this is n and operations, we'll call it ops here. Of n of 1, it's 1. 2, we get 1 plus 2 is 3. 3 is 6. 4 is 10. 5 is 15. Right, on and on and on and on and on. So then 6 is 21. 7 is 28. 8 is, plus 8 more, is 36. 9 is 45. Is that right? Yeah, we had 9. 10 is 55. Right, and on and on and on. So if we were to graph this out here, that is not a linear growth. Right? You get something that looks kind of like that. Is that? Maybe it's the other direction, sorry. This way. It's kind of like, looks kind of quadratic. Right? Think back to your math classes, that quadratic curve. Right? This is 1 and 1. This is 2, and it has to be at 3 already. Sorry, 3. My graph is kind of ugly here, sorry. So like 2 and 3, sure. 3 and 6. Or 6 over to there. Right? 4 and 10. You get the idea. Right, so you can see that this grows terribly, terribly slow for counting. Right, so it actually has some math here. So the number is, it's n times n plus 1 divided by 2. Right, that's the exact same thing we saw, right, for our fast operation, because it grows the exact same way. N times n plus 1 divided by 2. Well, if you remember back to your math class, right, we can factor or distribute here, so it would be n squared plus n divided by 2. Right, is this parentheses here? So that's n squared plus n, right, times 0.5. Again, we throw away coefficients. Remember, so anything that's a coefficient gets thrown away. We throw it away, and then we look at the biggest exponent here. So this is an n squared operation. So we'd say it's O of n squared here, because we're throwing away the coefficient and we throw away the smaller powers. You don't have to worry about the math too much. Don't sweat it if this doesn't make a lot of mathematical sense. Most of it's kind of hand waving. We take the biggest exponent here. So this operation then is O of, we got to return some. It is O of n squared. O of n squared. Or quadratic. Quadratic. That's probably spelled right. Yeah, I'll think back to your high school math. Fantastic. Okay. So in terms of growth rates. Right, there's a great chart in the book here. They're from bad to worse, right? So the best one is obviously O of 1, constant. That's an O. O of 1, right? That's our best. O of n, it's kind of in the middle here, right? O of n squared. Oops, sorry, over here. O of n squared. Let me slide this over a little bit, sorry. And probably the worst one is O of n factorial. And we'll look at some of those later. Also in here is O of 2 to the n. So O of n squared. So it takes n operations for every n that you have, n squared. This takes 2 to the n power of operations. This one's huge, and then n factorial is even bigger. Is having an exponential runtime one of the questions in a technical interview almost as bad as not solving it? You know, Noctis, no, I mean, just being able to solve it is good, and then being able to recognize that, yes, this is not an efficient solution is good. Right? And being able to work towards better efficiency, right? Being able to solve a problem is one thing, being able to solve it efficiently is another, right? And that's the sort of thing that's going to take some practice and some, it takes time. Nobody's good at everything. But if you can recognize that it's slow and understand that it's slow, that's huge for sure. Yep. So other things in here then that are between constant and O of n, you get things like, I can't write, I'm sorry, log n. Remember a logarithmic curve kind of looks like that. It's like an inverted exponential, right, where the exponential goes more like that. You're just sort of imagining it over a mirror of this like 45-degree angle. Right, it kind of gets mirrored there. So log n is pretty good, actually. That runs relatively quick because it's growing slower than your n. Right, so if you have 1,000 things, it's not going to take 1,000 operations. So log n is pretty good. A lot of times you might get a n times log n operation. N times log n, which is better than O of n because log n is less than that. No, I'm sorry. Nope. It's better than n squared. So n times log n goes over here in the middle because it's n operations, but it's n times the log of n. So slightly less here. It grows less fast. There we go. All right, so these are the pretty common ones. Constant, log n, O of n log n squared. Anything bigger than n squared, like 2 to the n or n factorial, are just huge. They're going to take a long time. Okay? So they go through all the math. Again, it's kind of nuts. You throw away coefficients, and he has all this ugly notation. Don't worry too much about it here. But this is looking at time complexity. All right. Yep. Let's see. I don't actually know anybody who uses LeetCode, like kind of questions, and in general, we're trying to get away from that sort of nonsense in the industry, but I'm sure some places still do. It's good practice just to know, solving efficiency sort of operations. It's like solving puzzles. All right. It's like a puzzle website. Code.com, I think. Yeah, algorithmic style questions. The world's leading online program learning platform. Sure. Okay. Yeah, I mean, some places use it, but I'm not sold on it as it being an actual good measure of a lot of things. Efficiency is important for sure, but it's not the only thing developers need to know. Okay, so now let's take a look at our linked bag here. So getting the current size, still, right? This is O of 1. Is empty, still O of 1. Adding an item, this one is always O of 1, which is nice. We don't even have our average time or our worst case time, right, being bigger. It's just constant because we throw a new node in there. It points to the old first, and then we have a new first. That's it. So this one is fast. There is none of that averaging that has to happen. There's no doubling that has to happen. There's no resizing that has to happen. Right. So our worst case for the array-based was you had to take n operations. But through our fancy math, we could say on average, it's still constant. This one is just always constant, average and worst. For removing a random item, right, still that's O of 1, takes one operation. To remove a given item, we have to look at n items. It might be in the beginning, it might be at the end. So on average, it's in the middle. Half of n is still O of n. So this is an n operation here for removing. Same for containing. Clearing, now this one is super fast because we just null the first. So this one is an O of 1, constant time here. O of 1, get frequency of, it takes n. Contains takes n on average, again on n here. To array, and O of n as well. So we get the same performance here with our linked objects as we do with the array-based objects. Again, except the add is, its worst case is better. But again, most of the time we don't really care about worst case. We can just ignore it. It's good to know, but you know, that sort of thing. Yeah, practice is good, Dusty. I mean, you know, research the company you're interviewing for. See what their kind of questions are. Sites like Glassdoor, you can people post the questions they get during interviews. Just see what kind of questions they're asking, and you'll know what to prepare for. More often than just, you know, sort of technical algorithmic style questions. When we interview for people, we're looking for more personal skills, project management. You know, can you get work done and communicate with people? Our company, we've got a general rule. It's a no brilliant jerks rule that we've stolen from Netflix. The idea is that if someone's brilliant but they're a jerk, they're going to cause more trouble at the organization than they're worth, and we don't want them. Right? So, you know, you could be algorithmically brilliant, but it's not the only thing we're looking for sure. And that's our organization. I can't promise all places are like that, and some places put up with that nonsense. Uber is apparently a terrible place to work. I would never recommend anyone go work at Uber, because they have a bunch of people who like to backstab each other and just try and climb this corporate ladder and all this nonsense. Where they did an interesting write-up in, I think it was the New York Times. They had one department was withholding information from the executive group to make the other department look bad. And it's just terrible, because like then they would get better bonuses or some nonsense. Like, just what a toxic place. That's awful. So, but you know, I can't say that's the same for everywhere. So, okay, so that's looking at how we would measure algorithmic performance. So this is all in terms of time. Okay, now we want to look at in terms of space. So in terms of space, that's how much memory is being used when an operation runs. So if we look at this one here, you know, the amount of memory we're using, we need a place to store int, or the sum, we need a place to store current, we need a place to store 1. But that's really it. So like that's 3 and the n here. So you're storing 1 integer, 2 integers, 3 integers, 4 integers. You're only storing 4 integers. So the space complexity is constant. We're only ever using 4 values. Same with this one, right? 1 value, 2 values, 3 values. A constant number of objects in memory. Constant number of objects in memory. So in space complexity, they're all the same. Right? They essentially use this. I mean, 4 is obviously less than 3, which is, or more than 3, which is more than 1, but it doesn't grow in size in terms of n. Right? We're not storing n things in memory to do something for these operations here. Right? What happens with our bag array, when we are increasing capacity, what we're actually doing is we are doubling our memory usage here. So because we're creating a brand new array and then we're copying all of these things over. So we're only copying the memory addresses over. So the actual items themselves that are being stored are not being copied. Just the reference to them is being copied. So we're doubling the amount of space we need in terms of memory addresses. Because remember, what an array stores when you're dealing with an array of objects here is you get a memory address. So like x324, I don't know, 344, x49b, x3fa, right? On and on and on. What you're storing is just memory addresses. This is where I go look up this object in memory. Those objects in memory don't have to be contiguous. Hey, the Red Phil, actually on YouTube, I actually taught a C++ course if you're curious. I'm sure there's other places online as well, but I've got my course on YouTube. So in a 64-bit system, each memory address takes up 64 bits. Is that right? That sounds right. It's definitely not bytes. Yeah. So, yeah, 64 bits. So we will address all of our memory. So in terms of how much space this is using, right? The objects don't move, but I need to build a new array with double the size of memory addresses, and so I can store 20 memory addresses now. Yeah. Gotta use those bot commands, otherwise Nightbot gets sad. So we'll use more space here because we have to double our storage, but the actual storage that we're using, essentially, most of the time, right, is going to be 64n, right? 64 bits times n objects. Right? And again, we get a throwaway coefficient. So it takes n memory to store n items, essentially, in terms of space, right? Now, what happens with a linked object, right, if we look at our linked objects here, is we're storing a node, which stores the reference to the item, and a memory address of the next node. So to store 10 things in linked objects, I have the address of the node, which stores the address of the item, and the address of the next node. Right? And we have another node, right, which stores the item address, which stores the next address. So a linked-based storage actually takes, right, this is a 64, this is a 64 for each node here, right? And then the node itself needs 64 bits to store it. That's only the first one, right? Because the next one is being stored here. So we actually take 2 times 64 times n bits, plus the actual size of the object. But again, the size of the object will be the same regardless of how you're storing it. So this one is actually worse here. Again, we mostly throw away the coefficients, but it does take up more memory to store things in a linked object manner because we have to store the reference to the item and the reference to the next node, versus an array, all the items are stored sequentially. So we know where the next item is because we know where we can find it in the array. It's just in the next location. What's up, Vivi? Yeah, I don't know if it'll work for you here, but we can try it. Have you? Hope you feel better. Had the 2 older middle kids got their COVID shots yesterday, and they're feeling yucky today. So that's been fun too. Usually they're the helpers when we have the cousins come over. All right. So in terms of space complexity, right, that's how much space we're storing here. So a common question we used to give in interviews, and it was sad how many people would fail at it. We'd say, look static, you want to give a character array, I'm sorry, a void method for a character array, and we'll say this is reverse. Given a character array. Nope, I don't know why I'm saying void. Reverse character array, I don't know, to reverse. Okay, or you say write a method reverse that reverses a character array that you were given. And what a lot of people would do is they'd say, oh, sure, okay, let's make a character array, size of to reverse, character array, reversed or something, reversed equals a new character array, size of to reverse. dot length. Right, and they'll say for index is 0, index is less than to reverse dot length, index plus plus. And they say, okay, let's go there. We'll take our reversed array at index of the length -1 minus index equals my to reverse at index. Right, so this is starting at the beginning here, going and then moving it to the end over here. The length -1 to get the last index minus the index. Right, so this will take every character from the first. Slide this up here. So if we gave you so that this was a character array, and I'll put Eric in, right? ERIC. We'd make a new array of size 4, and it'll put the C here, it'll put the I here, the R here, and the E here, and you get CIRE. Right? Well, how much space is this algorithm using? And then they would probably they would say return reversed. Right, so this wouldn't be a void method, this would be a character array method here, like this. Reverse. Sure, we could do that. And then, okay, well, what's the time complexity? Well, it's n operations, right? For every n letter, you need to move it. It takes n operations. Okay, sure. Well, what about the space complexity? Well, if you're making a new array, right, your space complexity, you're doubling your amount of space, right? 2x for space. Yeah, you could start with the end index and go forward, for sure. If you wanted to start at the end and go down to 0, either one's fine. If you want to avoid that -1, I guess. Sure. Okay, so 2x the space because you're making a new array. Well, can we do it better? Can we make it perform better? And that's sort of the challenge question. Okay, sure, you did the easy part. Can we make it better? Yeah, we could make it better, for sure. Well, how do we make it better? Well, we could use less space, right? Instead of making a brand new array here, right? We would loop through and we would say, okay, I've got a char, here's the temp character. It is to reverse at index. And then I'm going to take to reverse at index and assign it to reverse at length -1 minus the index. And then I'll take this location and I'll set it to temp. And then I can return to reverse. Right? This way we don't create a new array. We're not allocating any more space. So the space that we need here is for one temp character. So our space complexity is the temp character. Yeah, we're walking the array, right, using our index loop here. Do it without the temp. I don't actually, I can do it in Python without the temp, but not in Java without a temp char. And then, so actually, this is actually bad at this point here because we need to stop at the middle. So we need to stop when that is divided by 2. Right, because we're taking the end and swapping, going in one, swapping, going in one and swapping. So once we hit the middle, we need to stop. Right, so we only need to go up to length divided by 2. So this space complexity then is just an additional single character. No matter how big the character array is, we're only using an additional character swap. No, we're just reversing here, Sector Fox. Thanks for coming and hanging out, by the way. This just takes a single extra character in terms of space usage, and then in terms of complexity, it is technically faster because we're doing half n operations rather than n operations. So yes, that is faster. And sometimes if you want to argue specifically about efficiency, half of n is better than n, yes. But it's still in n operations, essentially. So it's better, yes, but not ridiculously better. Right? We didn't get it down to like log of n or anything. And you can imagine this would be important if my character array was like the book Moby Dick. If I took the entire book of Moby Dick and turned it into a character array, that number of n operations would probably matter. And if you can get half of that, that's a huge, huge savings, right? When we're talking about millions of characters, right? Is it even a million characters? I don't know. How many I'm curious now. Maybe we can Google that. How many characters are in the book Moby Dick? Is that even a thing we can Google? How many? Oh, probably not characters. How many words? Word count for famous novels? Here we go. Moby Dick. 206,000 words. And if you figure the average word had like 4, okay, so maybe not quite a million. All right, we're getting close though. Probably close to a million. And again, a million's pretty big, right? Look at that. Order of Phoenix beats out Moby Dick. Let's go, Harry Potter. Sure. Why is this a thing you can find online? I don't know. The internet is kind of amazing. Kind of amazing. Okay, so in terms of complexity, right, time complexity, we're still O of n, because we have to do n operations. And sure, half of n, better than n, right? So better to do half the work than to go from the beginning to the end. And then space complexity, right, we're using just a single character extra storage here. We're not making a brand new array, so this is more efficient in terms of space as well. All right, how's everyone feel about that? I know the text, oh, you don't need my chest there. The textbook gets a little bit mathy looking here, but that's sort of the idea of how we'll look at these efficiencies here. Cool. So this is usually everyone's least favorite chapter. Most of the math isn't too bad. You don't need to get super deep on it. If you get into a computer science degree, you'll get harder into this for sure. But for our purposes, right, best case, no one really cares because you're not often going to get best. Average case, yes, that is the most important because you want to know on average how long will this take me based on my n items. And then worst case, yes, still good to know, but we're not, hopefully won't get worst most of the time. And when we talk about sorting algorithms, worst will be more important as well once we get further into the textbook as well. You know, and maybe it depends on what you're doing there, Tochi. If worst is more important, I think average is definitely more important because that's what you're going to get most often. It's important to know the worst because you can get the worst. But you know, in terms of when we're trying to find a proper data structure for our solution, and this class is all about how do we look at the different data structures, know the different ways of storing data in memory, and figure out which one is the most efficient way to store our data to solve our problem. So before, like in 1500 or 2151, all you had to do was solve the problem. It didn't matter if it was a terrible solution or not. In this class, we're looking at how do we get a better solution, a more efficient solution. So we'll look at bag, we'll look at stacks, we'll look at recursion, queues, dequeues, or decks, priority queues, lists, sorted lists, searching, dictionaries, hashing, binary search trees, heaps, balanced search trees, graphs, all sorts of different ways of storing data and its impact on performance, impact on efficiency. Because what we're learning here in school in your programming degree is here's a bunch of tools in your toolkit. These are different ways you can solve problems. Now we're going to look at, okay, let's look at some more tools, right? Some other ways of storing data and how fast they are, because it is still important. Oh, that's fine, Tochi. This is actually OCC. I'm doing OCC classes this summer. Yep. Yeah, predictability is good too, for sure. Any other thoughts, questions? Brats or tacos for dinner? Ooh. I ended up doing pizza tonight because we ran out of time. Find out next time on Dragon Ball Z. Yeah, it's not Tuesday. You can't have tacos except Taco Tuesday, right? All right, any other questions about Project 1? And then one more push here for the tutoring through our Academic Support Center. You can book individualized tutoring for no additional cost. Again, the word free is wrong because it's paid for through your tuition and tax dollars, but no additional cost to you to schedule one-on-one tutoring. We've got two amazing tutors, Miss Rika and Mr. Tim. Both can tutor for $23.53, the data structures course. Mr. Tim is very familiar with me. He is actually the supplemental instructor for 1500 and 2151 for me. So he's been with me a couple semesters now. Or this is the second semester. I guess that counts as couple, being an SI for me. And he does individual tutoring. So he's familiar with some of my nonsensical projects and that's sort of the way I phrase things and whatnot. But Miss Rika is awesome. Miss Rika is awesome as well. She's been a tutor for a long time for our department. It's fantastic. Yeah, for sure. So I've got my individual office hours. I've updated here in the syllabus now. Thanks for filling out that when to meet. Monday and Wednesday from 3 to 4:30 p.m. or 10 to 11 p.m. And then by appointment as well. So if you can't make these standing hours, you're welcome to email me, contact me any way you want, and suggest a couple times, and I'll see if I can make one work or not. I can do Zoom. Like I know how to do Zoom. I tend not to use Zoom for classes. It's this lecture style format, and then no one wants to have cameras on, and we're just staring at blank screens, and you get the Zoom stuff. So I prefer doing stuff here on Twitch and Discord, and then you get to be anonymous as well, which is kind of fun. I actually did get some feedback in the course evals. I do read them, so that said they appreciated being able to ask questions anonymously. So, I mean, I hope you'd be comfortable asking questions anyway, but if being anonymous makes you more comfortable, that's fantastic. You can come in with a different username every week if you want. I don't care. Whatever is going to make it easier for you to make this material make sense. Because anybody can go buy the textbook, right? What I'm getting paid for and what you folks paid for is to have me help you learn it. That's kind of how I feel my role is as the instructor. Right? I'm not teaching it to you. I'm helping you learn it. Right? I'm showing you some of the things. I'm showing you the highlights. Here's the important stuff. Let's go over some examples, and then you can go read the book. Right? But I'm going to help you through it as we go. Okay? All right. So next week we're going to go over the solution to Project 1, and then we'll get into stacks, inheritance, and polymorphism. Our next data structure, the stack here, and then inheritance and polymorphism from the interlude, and we'll talk about the next project here. All right, and we're just going to keep on moving. We've got a project every 2 weeks throughout until we get to the midterm, July 14th, and then we'll work on the final project starting the 21st. We'll have a month to get that project done. Again, the final project is the bulk of your score here for the course. That's 40% of your score is this final project. The actual other projects make up 35%, the one midterm, and the chapter quizzes. You are not hyped about it. That's okay. You don't have to be hyped about it. I mean, they're projects. It's not always anything super exciting. But if you have questions, I'd encourage you to ask in the Discord, because when you ask a question, because you're not sure about something, I can pretty much guarantee someone else is not sure about it either. So just like if we were in class, you're asking a question out loud, someone else will see your question, they'll see my answer, and then they'll learn something from it too. Yeah, for sure, Mizuki. I mean, I think you should put all your major projects, anything that you can talk about and be excited about, and say, hey, this is, the things I learned, this is what I did, or this is my approach to it, is super interesting for asking people about it. Yeah, so the projects themselves, so the individual projects, 0, 1, 2, 3, and 4 make up 35% of your overall score. Hydration, oh my goodness, I'm out here. Oh, I got a little bit left here. Thank you for that. So any projects that you can talk about that you find interesting, I put on there. Just other than that, if you don't put any projects down, it's none. This was not beer. This was my iced coffee. And it does hydrate, doesn't it? I mean, coffee hydrates too, even though it's a diuretic, right? I still believe coffee is hydration. I'll drink my coffee and be happy. Okay, so we got after class tonight. I can hang out and chat. Yeah, I mean, water obviously is best, but So I can hang out and answer questions. We can hop on Discord, hop on a Zoom call, do some screen sharing, whatever you have. But general questions, definitely ask in the Discord. That'd be great. I think someone asked in the discussion about forming their own Discord. Yeah, you can go for it if you want, but I mean, you're welcome to use mine too, because if you have class questions, I can answer, other people can answer, that sort of thing. So yeah, up to you. So, and hopefully you've had a chance to find a learning partner from the beginning. Chat with them, right? When the link is in the syllabus or exclam Discord there. Boom, look at that. Oh, I beat you, Professor Burp. So talk with your learning partner. Again, you're welcome to discuss these projects with each other. The point at which you've gone too far and you're starting to copy off someone else or cheat off of someone else is when you have to take notes. And if you're just talking about ideas and, hey, this is the method I might have, or this is how it's going to look, or I'll do this sort of loop, and you're just chatting about it, that's great. Oh, Professor Burp. Nice. Yeah. It seems like it's been decently stable. It wasn't too bad, right? Inspector. I don't think it was too bad. No, I don't use discussions if I can help it. They're typically forced. So the discussion was just for a place where you guys can discuss, and it's only available to those enrolled in D2L, that sort of thing. Okay, good. Yeah, I had a couple blips here, but not too bad. Not too bad. Yeah, so you're welcome to discuss these projects, and then when we get to the final project, I'm typically would require it to be a group project, but again, we're not in physical meetings, so that you're not like sitting next to each other where you can chat after class, that sort of thing, and I'm not going to make you do it in the remote world. You know, everyone did professionally when we had to move remote, but it's just too hard to coordinate with everyone's schedule, so you're welcome to pair up for the final project, but you don't need to. Yeah, you can have multiple learning partners, that's fine. You know, a trio's okay. If you've got 4, then you should just do 2 pairs, but 3 people's okay if you want to do that. When it comes to the final project, if you want to work with 3 people, I'll have to give you more work. Typically, I'll let a single person or a pair do the same project, because you do have a little bit of additional work as a pair with all the collaboration and communication. Yeah, you can work by yourself for sure. I encourage you to work with a partner if you can, but you know, I'm not going to force that in our pandemic learning environment. So, yeah. And I did hear we still don't have any official word yet on the fall semester, but the plan is if the Michigan guidelines tell us we can be within up to 3 feet next to each other for that sort of distancing, and call that good enough if people are masking, whatever requirements we're going to have, we're hoping to be in person. If we can't get that close and we have to be at least 6 feet apart in person, we're not going to be able to make it work with the size of our classrooms. So like all of our computer rooms are only like 600 square feet. So you can imagine if you need 36 square feet for yourself, that doesn't leave a lot of room. Yeah, I know some people still want to be virtual. So I don't know. We sort of got a pass. Like our classes, there's usually an approval process to take a class online that we go through the accreditation process to make sure that it's quality and all sorts of things. And we got a pass from the Higher Learning Commission with the pandemic because everything just had to shift online. But moving forward, we're looking at doing more things flexible. So I know my classes will be in a flex format where my plan is I'll be in class in person if we're in person, and I'll still stream on Twitch. So if you want to come in person, you come in person. If you want to be remote synchronously, you come remote synchronously. And if you want to be asynchronous, fine, you just watch the recordings. Is the plan for how I'm going to run it. I'll be a little bit picky about the async option. Is if you're failing, I'm going to say that should not be an option for you. Like if you're not doing well, you should be coming in person. But if you're doing well, then I'm fine with whatever format people are going to prefer. There's a couple classes. So generally the basic ones, but you know, at OCC we only have 100 to 200 level courses. Over at U of M Dearborn, I've taught one of the more advanced classes in the data science program, but typically the intro classes. They're hoping to say before the fall schedule posts in June sometime. So I don't remember when they're going to post the fall schedule in June, but they want to have a decision before they post the schedule so that we can say, hey, this class is this class is this, this class is this. And then come fall, if it is remote or not, they should be tagged as remote synchronous or remote asynchronous versus just saying online or remote. So that'll be nicer in the fall. So at registration time, you will know without having to pester the instructor, hey, are you synchronous or asynchronous? Yep. Binary trees used in companies. So it depends on what you're storing, Noctis. It really depends on the data and how you're using it. A binary search tree is fantastic for managing sorted data. Definitely fantastic for sorted data. Yeah, I mean, just kind of depends on what data you have in memory and how you're using it. Hash tables are probably the most common because they're the fastest, and memory essentially is cheap. You know, it's usually easier to get a bigger server if you need more memory, that sort of thing when you're solving problems. But yeah, definitely in database tech, all sorts of interesting tree structures and that sort of thing. Oh, am I not following you, Professor Perp? All right, hang on. How do I follow you? I have to go to your channel here. Let's see. Let's check you out here. Where is it? Come on. It's loading. Where's my follow button? Oh, it's so slow.
Sounds like, well, I'll say is
There. Didn't I pause it? Why is it still going? Pause the ad. That's awesome. All right. I think I'm following now, my friend. You got it. Very cool. I should have watched the ad for you. I'm sorry. I could have had an adception. Yeah, so that's about it for tonight then. Chapter 4 is actually relatively quick if we hand wave a lot of the math. Not that the math isn't important, but for our purposes, right, we're looking at average case time and looking at, is it constant? Is it log n? Is it n? Is it log or n log n? Is it n squared? That sort of thing. A big OCC streamer following you. Oh, sure. Yeah, you could, yeah, say that if you want. All right, so why don't we go pester somebody else here, and then I'll hang around after. I can ask questions, answer questions in Discord, email me, text me, call me, whatever works best for you here. And I found if I change my screen here to stream ending, it doesn't lag so bad when I try and find someone else on Twitch to raid, because it's not trying to find anyone else. So it's been fun. If folks, let me know if you have questions. If you're welcome to ask questions about the project. Please do. Right, I'll help get you pointed in the right direction. Oh yeah, D&D night with Lantern Noir. We've got to go there. Always a fan of watching people play D&D. So we'll head over that way. Everyone say hi. Hopefully I typed it right. Yep, and we can head over that way. All right, folks, it's been fun. You take care. Please let me know if you need help with the project. We've got to get it in by 6 next week, so take care.